Gnanam Paramam Dheyam. Knowledge is supreme.
Recall that in the last lecture we proved that under the Galois correspondence of a Galois extension, finite Galois extension, the Galois intermediary field extensions will correspond to the normal subgroups of the Galois group of the original extension. We want to use this to prove that every finite abelian group will occur as a Galois group of Q, a Galois group of a number field over Q. That means what? That means I want to find a finite Galois extension of Q such that the Galois group is the given abelian group. And this problem is known as inverse Galois problem. So let me mention it here to start with. So this is known as inverse Galois problem. It is so given a finite group G. Question is, does there exist a finite Galois extension L over Q such that Galois group of L over Q is precisely the given G or isomorphic to G. This is a problem in general. This problem is a big problem and lot of research is done to answer this problem. It is expected that the answer is yes, and a lot of research is done in this direction and which uses algebraic topology, algebraic geometry and so many other connections. Also the theory of Riemann surfaces that is used in this kind of problem. So it is considered to be a very difficult problem. And I am going to answer this partially very special case of this we will prove today. Namely, if the given finite group is abelian, then I am going to construct a field extension of finite field extension L over Q such that the Galois group is precisely the given abelian group. So this is what I want to prove today. So we will answer if G is finite abelian. So remember, what is more important is Galois extension of Q, rational numbers. If one allows Galois extension of arbitrary field, then we can always do it. This I will show you in later lectures. And what am I going to use for this? The ingredients in this proof is the following: understanding the structure of a finite abelian group, that is one. So we will use these two facts. One, structure of finite abelian groups. namely if G is a finite abelian group, G is isomorphic to a product of cyclic groups. So G is isomorphic to Z mod N1 cross 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 Z mod NR for some N1 to NR non-negative integers, positive integers. So this is very standard, but we will also prove this. And remember that when I write this isomorphism, this is usually we are writing Galois groups as multiplicative groups, and this notation here on the right side is additive notation. So that one has to be little careful. This is second one is second ingredient. I will use it. Given any n in n non-zero natural number, we know that there exist infinitely many primes, prime numbers P with the property that P is congruent to 1 mod n. This we have proved this as a corollary to when we were studying cyclotomic fields over Q. That time we have proved this, and we will use it today. So let us now state it formally and prove it. So theorem, this theorem I am going to prove is, let G be a finite abelian group then there exists a field L such that L which contains Q such that L over Q is a Galois extension with Galois group this equal to the given group G. This is what I want to prove. All right. So proof. Note that we have proved that if I take, so if I take the Galois group of the cyclotomic field extension, this is isomorphic to Z mod n cross. This is what we have proved, and I am going to use this fact also. So if you want, this is the third fact we are going to use. All right. So remember that in the last lecture I have also proved that if I take the subgroups here, that is subgroups here, and the intermediary field extensions, they are in one-to-one correspondence. The Galois correspondence, I am going to use the Galois correspondence. So what is that Galois correspondence? It says that, so Galois correspondence this is also we have checked. So on one side, intermediary field extensions of the cyclotomic field extensions over Q and the subgroups of the Galois group. This there is a one-to-one correspondence. Given a field extension in between here, that is M, that corresponds to the not gal M over Q, H is gal Qn over M. This is clearly a subgroup here. And how do you recover M from H? This is the fixed field of H. This is it. So now the idea is the following. I have given a finite group G. So I have given G. I want to realize this as a subgroup here. This I know. This Galois group we know. So this is same thing as subgroups of G mod n cross units modulo n. This is this. So I want to realize this G as a subgroup here. Once I realize that, I will get hold of extension M, intermediary extension here. So this will corresponds to that M, and when will M over K be Galois? That is what we have checked last time. M over K, this extension is Galois. That is if and only if the subgroup here should be normal, but we have an abelian group. So G is always normal here. So this M over K will be a fixed field of this, and the G will be realized as therefore Galois group of M over K. So this is the fixed field of G of Qn. So that is how I will do it. So therefore our problem is, given a finite abelian group, I want to realize it as a subgroup of Gn cross. Once I do that, I will use this Galois correspondence, and that will give me a fixed field, and this fixed field is to check this fixed field over, this is over Q. This fixed field is Galois over Q. To check that, we would have to go back and check the G is normal. But normality is obvious because our field extension, our group, Galois group of this cyclotomic field extension is abelian. So that is the plan. Now given G, I want to realize this as a subgroup of Gn cross. That is the main step in the proof. Okay, so that is how I will use that corollary, that there are infinitely many primes. So first of all, by first step, I know because G is a finite group, G is a product of cyclic groups. That is this. This I will prove it after I finish this proof. So this I will prove. This is by this is the structure of the abelian group, finite abelian groups. Okay. Now what do the second say? Second say that given any integer, any natural number n1, I will find a prime number p1, so that p1, so given n1, n1 is a non-zero natural number, so choose p1 prime number with the property that p1 is congruent to 1 mod n1. But this is equivalent to saying n1 divides p1 minus 1. So that means what? That means if you look at this group, so this further implies, if I look at the group Z mod P1 cross, this is a cyclic group. This is a cyclic group, and this n1 divides P1 minus 1 means this cyclic group has a cyclic subgroup. Subgroup of cyclic is cyclic always. So because n1 is a divisor of the order of this group, there will be an element of that order there. So that means there is a cyclic subgroup of orders n1 inside this group. So that means this cyclic subgroup of order n1 is always isomorphic to Z mod n1. That means this Z mod n1 is a subgroup of this. This follows from this, and the knowledge that this is cyclic. So given any cyclic group and divisor of the order of that group, there is a cyclic subgroup of that order, and every cyclic subgroup of that order will look like Z mod n1. So therefore this. Now given n2, I want to choose a prime number. Choose P2, which is different from P1, with P2 not equal to P1 and P2 is congruent to 1 mod n2. This I can do it because I know there are infinitely many prime numbers with this property. Therefore, this is only one, and I choose a different one now. I want to avoid this P1, and such that this is equivalent to saying again n2 divides P2 minus 1, and that will mean that Z mod n2 is a subgroup of Z mod P2 star, P2 cross. Same argument as before. And I keep doing this to this given n1 to nr. So therefore I have now for the rth number nr, non-zero number nr, we find a prime number pr prime, which is different from earlier chosen primes. Pi, I is from 1 to r minus 1 with the property that PR is congruent to 1 mod NR. This is possible because we have proved earlier that given any natural number n, there are infinitely many primes, so that P is congruent to 1 mod that natural number. This congruence is equivalent to saying that NR divides PR minus 1. So this means in the cyclic group PR cross, ZPR cross, this is a cyclic group of order PR minus 1, and this NR is the divisor of this. So it has a subgroup of order NR. So that is also cyclic, because cyclic subgroup of a cyclic group is cyclic again. That is additive notation. So this goes inside this. Now let Qi be the number Pi minus 1 divided by Ni. We know Ni divide Pi minus 1. This is for I equal to 1 to R. And now since Z mod Pi cross, this is the multiplicative group of a finite field, which is, we have proved it is cyclic of order Pi minus 1, and Qi divides Pi minus 1. Therefore there exists a unique subgroup Hi of Z mod Pi cross with cardinality of Hi is precisely Qi. This is for I equal to 1 to R. Therefore, what do we get? This Hi is a subgroup of a cyclic group, therefore Hi is also cyclic, and then we know that Z Pi cross modulo Hi, this will be cyclic of order Ni precisely, because Pi minus 1 by Qi is precisely Ni. So this is Z mod Ni. This is because since Z mod Pi cross mod Hi is cyclic of order Ni. Therefore, these any two cyclic groups of the same order are isomorphic. So, therefore, it is this. Now, you look at Z cross of P1 to PR. P1 to PR are the primes we have chosen. This is by Chinese remainder. This is isomorphic to Z mod P1 cross Z mod PR. This is by Chinese remainder theorem. So, this proves what? This proves that Z mod n cross n is this product of these distinct primes. So, this modulo H1 cross HR, this is isomorphic to Z mod P1 cross H1 cross Z mod PR cross mod HR, but this is precisely Z mod N1 cross Z mod NR. This is precisely our group G, given group G. So, we have proved that a given abelian group is isomorphic to the quotient of Z mod n cross for some n, that is what we have proved it, where n is this product of these distinct primes. So, and remember what we want to do is we want to find an abelian extension, we want to find a Galois extension of Q with precisely Galois group G. So, now you take, we got hold of this group H. This is our group H. H is the product of this group, which is a subgroup of Z mod n. So, let Q n over Q, this is a cyclotomic field, extension of Q. These are precisely Q n is precisely Q zeta n, where zeta is the primitive root of unity, and then in that we are taking M to be the fixed field of, we know that the Galois group of Qn over Q, this Galois group is precisely Gn cross, and in this there is a subgroup H. So, we can take a fixed field of that. So, let M be the fixed field of with respect to H of this Qn, then this M is the intermediary field, and I want to prove now that Q M over Q is Galois extension with Galois group G by the Gal Q power n over Q modulo H, which is nothing but G mod n cross mod H, which is the given group G. So, we have to justify this is a Galois extension with Galois group this, but that is immediate because we know this extension Q power n over Q, this is an abelian extension, abelian with Galois group G mod n cross, and H is a subgroup here. Therefore, H is normal in G mod n cross because it is abelian. and therefore we know that this is what the criterion for fixed field fix H Qn over Q is Galois with Galois group G mod n cross mod H, which is our given group G. For this we have used Galois correspondence. Namely, the normal subgroups will correspond to the Galois sub-extensions. So, that proves that given any finite abelian group, we have a Galois extension of Q for which the Galois group is the given abelian group. So, this was a part of the inverse Galois problem for finite abelian groups. Here one can also invoke the big theorem structure of finitely generated abelian group, but in this case it is not really necessary and the proof is really simple. So, I want to indicate this proof. So, all right. So, the theorem I want to prove, that theorem, this is structure of finite abelian groups. So, let G be a finite group, finite abelian group. Then G is a direct sum. Remember, because we are dealing with finite direct sums only, because G is a finite abelian group, finite direct sums and finite direct product, they are same. Direct product of finitely many cyclic groups. This is what I want to prove. All right. So, that means, and all the cyclic groups will be isomorphic to Z mod n1, Z mod n2, etc. Therefore, that proves our assertion that we have assumed. So, I have to prove this. So, proof. All right. This proof is very interesting proof. This is due to Shenkman. There is a very nice book by Shenkman, group theory, but it is a little unusual book because it is quite difficult to read. All right. So, because we have G is a finite group, choose a natural number n such that G is generated by these elements x1 to xn. If G itself is cyclic, then I could choose n equal to 1, and G is cyclic and we have nothing to prove. So, we could assume that n is at least 2. This is we may assume. All right. So, G is generated by n1 to x1 to xn. Now, I am going to choose the generating set. So, choose among all generating sets, among all generating sets x1 to xn of G, choose the one, choose a one with n least possible. There may be many generating sets. Among them, you choose the one which has the least number of elements. Okay. Now, among them, further among them, choose a one such that the first element, such that x1 say is of least order. So we have chosen a generating set which has n elements and n is at least 2. So look at the generators x1, x2, etc. so on. Look at their orders. So one of them will have the least order, and among all the generating sets we have chosen, choose the x1 which has the least number of order. So the order of x1, which is, let us call this as, what did I call it, m, least. Right. So G is generated by x1 to xn, and this one has order m, and this one is the least. Remember, according to our convention of order of an element is always a positive, non-negative integer, and in this particular case, because G is a finite group, obviously the order of all elements are positive. No element will have order 0. Remember, order 0 means the subgroup generated by that has the infinite order, which is not possible here, because G we are working in G is a finite group only. All right. And what is it we want to prove? We want to prove that G is a direct sum of cyclic groups. So I want to let H be equal to subgroup generated by x2 to xn. This is the subgroup of G generated by x2 to xn. All right, and I am going to prove the assertion. So, what assertion? We are going to prove, we will prove our assertion by induction on the order of G, cardinality of G. This is order of G. What assertion? That G is a finite direct sum of cyclic groups. This assertion I am going to prove it by induction on the order. Now remember that the H, the subgroup H is a subgroup here, and what we have dropped is an element of least order, and that cannot be. So the least order element x1, x1 is m. This least order element cannot be identity, because if it were an identity element, then our set is not a minimal generating set for G, but we have chosen first a minimal generating set, and among them the orders of the generators, the x1 is the least element, order of x1 is the least element. So therefore this m is positive, and therefore this cardinality of H is strictly smaller than cardinality of G, strictly smaller, because x1 is not in H, and therefore the theorem is true for H. Therefore H is a direct sum of cyclic, H is a direct sum of finitely many cyclic subgroups. This is induction hypothesis. Therefore, if I prove that the G is a direct sum of cyclic group generated by x1, direct sum H, if I prove this, so this is what we will claim. If I prove this claim, then we are done, because this is cyclic already by notation. This is cyclic group generated by x1 and H is the direct sum of cyclic finitely many cyclic subgroups. So, G will be altogether direct sum of finitely many cyclic subgroups. So, only have to prove the claim. So, proof of the claim 11, this is proof of claim. So, I have to prove two things. G is the sum of these two groups, and I have to prove that they don't intersect other than identity. X1 intersected with H is only the identity element, which I am denoting by 1. This is what I have to prove. So, this one is obvious, because H is generated by x2 to xn, and G is also generated by, this is same thing as generated by x1, x2, etc. xn. This was given to us already, we have chosen like that. So, I have to prove only this. So, let us take element which is common. So, let us take Z belongs to here, and we want to show that this Z is actually 0 element. This is what we want to show. So, look at Z. On one hand, if Z is non-zero, we should get a contradiction. So, on one hand, Z is a multiple of x1. I have written the groups as additive groups. So, therefore, this identity I should write it 0, not 1. So, Z, if Z were non-zero, on one hand it is a multiple of x1. So, Z will be A1 times x1, adding x1, cyclic subgroup generated by x1 means adding x1 so many times. On the other hand, it will also be an element of H, so it will be a Z linear combination of elements from x2 to xn. So, A2, x2 plus 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 an xn, where A1, A2, etc. an, they are integers. All right. Now, let us take D to be the GCD of these integers A1, A2, etc. an, and divide. So, once I take this, then what do I get? Then let us call G, element G, which is by definition I am writing it as minus, I want to shift this term to this side. So, that will become minus A1 by D x1 plus A2 by D x2, etc. plus An by D xn. Consider this expression. This is an element in the group G. Alright, and if I multiply by D, what happens? So, that means if I add G, D times what happens? D times G is nothing but minus A1 x1 plus A2 x2, etc. plus An xn. This element is 0 because we have taken this as Z1 and then I have subtracted. So, this is 0. That means what? That means the order of G1, order of G, order of this element G, what can it be? It has to be smaller than equal to D. This is smaller equal to D, and D is smaller equal to, D was a GCD. So, this is smaller equal to A1, and A1 is strictly smaller than M because you see Z is A1 times x1 and x1 this is m is the order of x1. So therefore, if this a1 were bigger, then I could always reduce it to the smaller element. So therefore, we have this a1 is smaller than this, and order of g is bigger equal to 0. So therefore, I found an element G in the group G whose order is strictly smaller than that M. So now if I could check that there is an element, so the G, if I can find a generating set with G here, G is y1, y2, yn. If I can find such a generating set, I will get a contradiction to our choice of a generating set where one of the element has order strictly less I found. So we claim that now, we claim that there exists y1 to yn in G such that this is a generating set for G, which will contradict our choice of that M. That M is the least among all orders of the elements which is the generating set for G. And what is this? This is very simple. I will just state it as a result and then one can prove it very easily. So the result is the following. So which follows from the following? This follows from a simple fact. So what is the fact? So that is, I want to write it as an exercise. Let G be a finite abelian group generated by x1 to xn, and let a1 to an are integers such that this linear the GCD of a1 to an, this is n, this is 1, then there exists y2 to yn in G such that G is generated by, first element is this linear combination a1 x1 plus 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 an xn comma y2 comma yn. This is G generated by this. So that is precisely what we wanted to prove, because in our case G is this linear combination and the GCD is 1, because this D is the GCD of a1 to an, and therefore the GCD of this coefficient is 1. Therefore, I will find a generating set where G is one of the element. That is what we wanted to claim. So this is a very simple exercise. This follows from the fact that whenever you have n integers, if the GCD is 1, 1 is a linear combination of those elements. 1 is a Z linear combination of a1 to n. That is precisely the meaning of GCD is 1. So using that, one can prove this exercise very easily by induction on n. So I will leave that proof for you to check, and with this I will end this lecture, and next we will continue our discussion on the Galwa groups, the next one. Thank you.